All right, so I'll hit the record. So I know I missed the first like 3 problems or something, right? But there we go. This one is really tricky, if I'm being honest, because you have to put a hyphen between 60 and 7. And if I'm being honest, I don't know if I would have got that if I hadn't. Like if you said 67 thousandths, that's plenty good for me. That is like such a minute little detail to put that hyphen. But when you put like basically you put the hyphen between, I guess, your tens and your ones digits when you have a compound number like that. Like 21 or 31, I guess there's a hyphen. Is what it seemed like. Shows you how much I pay attention to that rule. It's the age of autocorrect. Okay, so full question. I think this is the last one for this first one. There might be one more, so don't hold me to that. It's the same deal, though. Woo! Tens, hundreds, thousandths, tenths, hundreds, thousandths, 10 thousandths, 100 thousandths, millionths. Okay. That is a lot of counting. But I think hopefully maybe you heard me. We're going tens, hundreds, thousands, 10 thousandths, 100 thousandths, millions. Did I count it right? Oh, okay. Did I count it right? Tenths, hundreds, thousandths, 10 thousandths, 100 thousandths, millions. That's it. Then you go to 10 millions. I believe it should be in millions, though, right? There should be 5 zeros if we're moving over 6 spots, and there's already one number there. There's 5 numbers we got to account for. Oh, look at y'all. Good job. 3 millions. All right, so question 23. My hard drive has a capacity of 1.2 terabytes. Ooh, excuse me. And tera means trillion. So this is saying 1.2 what? Trillion bytes. So in these, it says using scientific notation, rewrite the following statements using a number in scientific notation. So this is the way I input the answer into here. I did what I said don't do. I used an X sign for multiplication. But your answer should look something like this. It should be some sort of number in scientific notation. So I use the caret for the exponent. So we want to rewrite this as, basically we're writing it as 1.2 trillion in scientific notation. So think about how many zeros a trillion has. We're going 3 to get to 1,000, 3 more to get to million, 3 to get to billion. Trillion should be right after a billion, I believe. Three to get to 1,000, 3 to get to your millions, 3 for the billions. Oh, crud. My answer's going to be way wrong. I just started typing it and then like got my fat finger on the submit button. All right, so this number should be 1.2. And we're multiplying it times 10 to the what power? Where are we at? Come on, silly dog. All right, I'll give you like 10 more seconds. We gotta get through this problem though. Yeah, I definitely got it wrong. Like I said, I just started typing in my answer, then it said submitted. I was like, well, that's definitely not correct. 1.2 times 10 to the 12. That's right. What else are we saying? 1. Psh, get out of here. Yeah, that's it. Right here, this is it. Oh, no, that needs to go up in power. But you need multiplication here. It needs 1.2. There should be an X right here between these things. Yeah. Trillions should get you to the 12th. Billions should be what, 9? Millions is what, 6? Is that right? Okay, so what is this question? Diameter of a typical atom is about 0.5. Okay, so they want us to write this in scientific notation. Let's go down more. Okay, that's it. Never mind. The diameter of a typical atom is about 0.5 nanometers. Recall that nano means billion. Okay. Think about what billionth is. Tenths, hundredths, thousandths. Ten thousandths, millionths, millionths, millionths. What is that? 8 places? Is that right? 10, hundredths, thousandths, 10 thousandths, 100 thousandths. Then we go into the millions. We go into 10 millions, 100 millions. Billions is 9, I think. Is that right? 10, hundreds, thousands. And then for scientific notation, remember there's got to be just one number out in front of the decimal. So it's got to be to the left of the decimal. Where's the hat sign? There it is. Right after the percent. Okay. Hope I got, yeah, I got the right number. Okay. Sounds like it. What are y'all saying? What are we saying? 5. Are y'all giving me the 0.5? Is that what y'all did? I'm glad y'all did this. I'm so glad y'all did this. Yeah, so it should be -9. But here's the thing. We have 0.5 times 10 to the -9. That's half of a billionth, right? There, that's the 0.5 of the billionth, or the nanometer, the 0.5 nanometers. If we have, let me get my annotation. Here is what I'm trying to do. Get some text up in here. If we have 0.5 times 10 to the what power? -9. I want to talk about how to get from like this thing to the scientific notation. So scientific notation says that we have to have one number out in front. And so this is the sort of approach I take to finding it, and it's the thing that makes sense in my head. But what I'm looking at here is I don't want to change this number. So I'm looking here. I now want to multiply this by 10 to the something power, right? To keep it in scientific notation. What I don't know is my exponents on my tensies. So what the way I kind of look at it is I go from 0.5 to 5 here. And so this is getting larger. So guess what? This thing has to get smaller if I want to keep it the same. So in order to get it smaller, I have to get it, subtract it by 1. This is moving one place to get larger. This is moving one place to get smaller. And so that's sort of how I convert these scientific notation in my brain when you have to convert them. Sometimes you have to convert them like 1 or 2 decimal places after you do some operations in order to keep them in scientific notation. Like this one, right? When we have a fraction. So this sort of thing comes up quite often when you're working with scientific notation. All right, so that is that one. This next one, perspective through estimation. Use estimation to make the following comparisons. Discuss your conclusion. Which is greater? Okay, so this is going to be something you're going to have to talk about. I'll do a little bit maybe of a breakdown. But which one do you think you spend more on? Transportation or food? Oh, shoot. I meant to answer more to that one. I can still. Huh? This one is going to be something that's just like personally, like, I don't know. And maybe you don't even know. Just like kind of guess. Like, which one do you think you spend more on? Transportation or food? It's all going to depend how you transport yourself on or how you eat, basically. You think the amount you spend on food? I would say for me, probably transportation. If you take a 25 car, what? I think is what it was. If I take a 25K car, 25 is about average car, and maybe you get like what, 10 years out of that. I think I'm already at 208. So what I'm kind of doing in my head to think about this is I'm thinking about my car is about 250K or 25K, not 250, sorry. And I'm dividing that by 12 times the number of years. So if my car lasts, what, 10 years? That's 120 months I have to divide that by. And if I did this, I think I got somewhere around 208. That's probably about how much I spend on groceries, like 300 probably is the max in a month. I think when I was looking, it was like between 150 and 300 is how much most people are spending on groceries. So if I'm just looking at my car payment by itself, my car payment's already getting me there, right? My total value of my car divided by how long I'm going to have my car. Each month, I'm going to probably pay 208, something like that. So already my car payment's already pushing it, right? So I would say probably that's not even including gas or wear and tear. So I would say definitely for me, mine would be transportation. But that's one of those things. Give me some numbers on something you spend. I don't know. Try to think about those things. This is what they're trying to get you to do. And I know like a lot of these things, a lot of you are still seniors, right? So when you start living on your own, you start noticing prices a little bit more. Energy comparisons. So table 3.1, when we measure energy in joules, we can just kind of compare joules to joules. It doesn't really matter how we do it or what sort of system is being used, whether we're running and using joules or burning something like coal and producing joules. We can compare those sorts of things. And so we can come up with some wonky examples of comparing, I don't know, running to burning a kilogram of coal, right? But what does this ask? I guess that's what I should see. How many average candy bars would you have to eat to supply the energy needs for 8 hours of running? So here's the deal. I would do unit analysis with this. This table kind of gives you a conversion factor, right? That's the way I sort of see it. 1 hour of running. Energy needed for 1 hour of running looks like 4 times 10 to the 6. Is that what that is? Joules. So you should be able to write a ratio, right? On one side of that ratio should be 1 hour of running. On the other thing should be 4 times 10 to the 6 joules. And I do have these broken down a little bit more. But how many candy bars per hour of running? And then that's what I would figure out first. And I think that's what I did. I figured out how many candy bars per hour of running using this table. And then I figured it out for 8 hours of running. One candy bar is 1 times 10 to the 6. I know that's a little bit blurry on this, maybe. And these are all measured in joules. Oh, I remember this one. I was just like, I don't need to work it out. Oh, paper. Candy bars. Oh, man. Johnny has 10 pieces of candy and he eats 5 of them. What does he have? Diabetes. That's what I'm reminded of. It's just like, let's eat these candy bars to run. And so just to look at this table, this is energy needed for 1 hour of running is 4 times 10 to the 6. And the energy from one candy bar is 1 times 10 to the 6. So they're kind of nice on these because they're giving you powers of 10 that kind of match. Okay. This one is a difficult one. So I've tried something, I'm happy. What'd y'all try? 32, 32. 32 times 10 to the 12th. I know what you did there, but it's a little bit easy, I think. Yeah, okay. I think, yeah, the next slide I got it worked out. That's right. I was going to say I did, and then I double doubted myself. All right, so one candy bar I know is like 1 times 10 to the 6 joules. This is what I was talking about. I think most of you got this far. I'm trying to see where you got 40 from. I'm not sure I'm seeing that. Maybe you did 1 extra hour or something. Or you did 1 extra here. 1 hour of running is 4 times 10 to the 6 joules. So this is sort of like what I'm talking about with the unit analysis. I have a puzzle piece sort of here that I need to fit these things together. And I need to fit these things together so that joules end up canceling out. And I probably want candy bars on top and hours on bottom is what I'm thinking. And so there's one sort of way to do that. I put this one down first, and then I flip this one. So my joules are on top here. My hour of running's on the bottom. So I think a lot of y'all figured out I'm getting 4 candy bars per hour. I think the one that said times 10 to the 12th, I think you flipped one of these is what happened, and you ended up adding them, which you did beautiful. Like you did the correct process for like adding your exponents there, right? That was correct. You just flipped up one of these things, but should be in this order. You should get 4 candy bars for every 1 hour. So for 8 hours, I believe that should get you up to 32, right? Any questions over this one? Are we seeing sort of how these puzzle pieces fit together? Hopefully, like this guy's joules and this guy's joules are going to end up coming off of there, right? We want to set it up so that those things simplify out. And then when we have it in candy bars for every 1 hour.
So is the 10 to the 6 gonna cancel out as well?
Oh yeah. I don't have it on here, but this is on top. This is on bottom. So it's like we have 1 10 to the 6 on top. Sorry, it's trying to draw this stuff with a pen in my little scroll pad on my. Okay, but yeah, it's like a 10 to the 6 over the 10 to the 6. This is just a big fancy 1, right? Absolutely. And so because they are the same number, yeah, they will simplify out, and we just get 4 over 1. So, and I talked about it in the notes, but we can kind of look at the powers of 10 kind of separately. We can pull them off through the like operation of multiplication, and we can look at the number, and then we can look at the power of 10 sort of separately, right? And I think I did that in one of these coming up. It comes kind of full circle, hopefully. How many liters of oil are required to supply the electrical energy needs of an average home for a year? How many liters of oil is what they asked? Is that what it was? How many liters of oil? So the two numbers we're looking at here, I believe, are 1.2 times 10 to the 7 joules is for 1 liter of oil burning. And the electrical energy used in a house daily is 5 times 10 to the 7th. So this is my sort of advice, because this one is pretty involved. Find how many liters of oil you would need for a home each day. And then once you find that, you need to find it for the year. So then you're going to multiply by 365. But yeah, that almost tripped me up when I was answering this problem. So it's like when people warn you about something, they're usually warning you about something they did. But definitely want to multiply it by 365 after you get the daily use, so that we can get to the yearly use. Okay. Did I do that right? I feel like that one's done. Yeah, that one should go. 1.2 times 10 to the 7th is the 1 liter of oil. 5 times 10 to the 7th is the energy for 1 home daily. That looks better. That's all right. Does it say what to round it to? Round it to the 10th place. I think that'd be good. So I would really try to set it up so that you end up with liters of oil per home, right? Per home daily, I guess. And so I think if we find that rate first, that's probably your first step. And you can do it with these two numbers and these two conversions. So we want liters of oil per home daily. And that'll give us the daily rate. After you do that, multiply by 365, it'll get you the yearly. Oh, man. Oh. I'm going to find a good masseuse when all the stuff is over. I'm kind of needing to go to one, but don't want to really risk it right now until everything's simmered down. The numbers do look like they're going down, though. There's a little bit of glimmer of hope, I feel like. They're receding back to what they were, so I wouldn't rejoice too much and go out and celebrate like some of these people, but it looks like we might start returning to normalcy at some point. Pretty soon, hopefully. All right, so give it an attempt. Do something. Even if you have no idea, throw a number down. Try something out. It's probably me. I probably forgot to hit submit. No, who's that? Ricardo? Who are you? Stephanie? Are you working on it? Am I rushing you too much? There we go. Oh, okay. What'd y'all do? Did y'all not round it or something? What'd y'all do? 1520. It looked like you got the right number. It looked like maybe, yeah, that 1520 is the right number. Okay. 2190. I'm not sure where I'm seeing where that one's coming from. Yeah, I think you just like messed up with your 10 powers there. So how many liters of oil for home for a year? So 1 liter of oil gives me 1.2 times 10 to the 7th. So this is the way you should have probably set it up. And yeah, someone keeps adding these. If they're on opposite sides, right? If one's in the numerator and one's in the denominator, I have this on top and I have this on bottom. They are the same number. They are essentially just one here. So I really don't even have to pay attention to my powers of tens if they're the same number. And I got one in top, one in bottom. Those things should simplify out. But this should be giving me what? 5 over 1.2. So I have that there. 5 over 1.2, which gives me somewhere around 4.1. Ooh, excuse me. 6 repeating. And this is the daily use. If we want their yearly use, we have to multiply this by what? 365. So it should give me somewhere around 1520 liters is what I was looking for. Questions about this? Okay. Yeah, so this is like I was saying with that unit analysis. I wouldn't try to lie to you like this. Unit analysis really comes in handy on a lot of stuff. And I've been doing it over a dozen years. So if it seems like if it seems intimidating or something, like it's like, man, I'm only good because I've been doing it for so long. Don't freak out. If you could generate energy by fusing the hydrogen in water, how much water would you need to generate the electrical energy used daily by 10,000 typical homes? Round to the nearest thousandths. Fusion of water, 6.9 times 10 to the 13th. Electrical energy used in an average home daily is 5 times 10 to the 7th. I'm wondering if that's like, oh, there it is. US, yeah, because US annual energy consumption is way different from the world's, right? We use way more energy than a lot of countries. There's a lot of phantom power and stuff that we have. It's kind of stupid. 6.9 times 10 to the 13th is how much you're getting from the fusion of 1 liter of water. And average daily use in a home is 5 times 10 to the 7th. So this one, our powers on our tens are not the same. So we're going to have to end up doing maybe a little bit more figuring with those numbers. And so I think the approach is to find out how many liters I need for one household daily, and then figure that out for what, 10,000 households? Was it 10,000? 10,000 homes, yeah. That, and I just did these problems like not that long ago when I made this quizzes. So I might have slightly an unfair advantage to getting these things done. Energy needed from one house. Daily is 5 times 10 to the 7th. I think that was it. Let's see this thing where to go.
I have a question.
Yeah, what's up?
Do you write in scientific notation or standard?
I have it in standard because I think I say round to the nearest thousandths.
Okay.
And I think there's one number that you should put there if I remember correctly. The other one should be 0. Like that is the nearest that you'll probably get. This one is pretty involved. It's like equally as involved as the last ones, but now we have a little bit more, how you say, number crunching in there, you know? Did I get it right? That's such a weird sound. I don't ever know what it does. It gave me incorrect. Why did it do that? I forgot to put units on there. Whoops. Oh, I need to exit out of this full screen. It should be 0.007. What are we saying? 0.001 is a little low. Oh man, we are all over the place. Okay, let's look over this one. Next one. So there we go. Maybe I did this a little. I didn't do this the same way I told y'all to do it, I guess, huh? But we have 5 times 10 to the 7th joules for every 1 house. So if I want to know how many total joules I'm going to need, I think I did what, 5 times 10 to the 11 joules needed. And so I know I need this total many joules for 10,000 houses. I know every 1 liter of water will give me 6.9 times 10 to the 13th joules. So the way I set it up is that when I multiply this by this, I set it up with my joules on bottom over here so that my joules would cancel joules on top over here. This is going to give me total liters of water that I'm going to need for the 10,000 houses. And I didn't write it, but if you wanted to, oh, come on, annotation. You could write all this thing over 1, right? If it's confusing you, maybe put this over 1. But this 5 is on top. The 6.9 is on bottom. So at some point, you should have really divided 5 by 6.9. If you didn't multiply by this 10,000 first, these numbers would be a little bit different. Because I did it a little bit differently whenever I worked it by hand than when I did it in my notes here. But I still got the same solution. It still should be this moved over 2 decimal places. It should give you 0.007 joules. In my notes, I didn't do this. I just got those 2 numbers. So annotate. Maybe here. I did like 1 liter of water to like what? 6.9 times 10 to the 13th. So this was one of my fractions, and the other one was joules on top, so 5 times 10 to the 7th. So there are multiple ways you can sort of work these things, is what I'm trying to sort of get at here, right? 1 home daily. So I multiplied these 2 things, and then I multiplied by the 10,000 is what I did in my notes. So draw, come on. So I want, this is 1 fraction. I'm multiplying it by this fraction. So, and then multiply this by the 10,000 homes, which is the same thing as 10 to the 4th power. So I still did the 5 over the 6.9. So even doing it this way, I'm getting 5 over 6.9. I'm getting 10 to the 7 minus 13 plus 4 is what I'm going to end up doing. I'm taking this 7, I'm subtracting that 13. And then when I multiply by this, I'm also have to add 4 back to here. So I'm maybe combining all those things in one step. I should probably split them up a little bit. But it's just powers of 10 is what I'm kind of accounting for here. Questions about this one? So there are different orders you can work these things in. That's kind of like why I put so much emphasis on unit analysis. And like, I think I showed that when I did that back in that chapter. Like a lot of times I don't know what the heck I'm doing, but like the unit analysis kind of tells you. There were approximately 2.69 million deaths in the US in 2015, expressed in quantity and deaths per minute. So just in case you didn't think we talked about anything positive in this class, here's your counterexample. We have deaths, and this is in 2015. They're talking about in the year. So this is deaths per year. We want to convert this to deaths per minute. So 2.69 million for every 1 year. And we want to go to minutes. So I think we're going to have to use the fact that there are 365 days. These are things you should know, right? You should know these conversion of 365 days in a year. You should know that there are 24 hours in a day. You should know that there are 60 minutes in an hour, 60 seconds in a minute. Okay, and I believe I have this to the nearest 2 decimal places. I believe. Is that what it says? It doesn't say. Oh, it's an upside down turtle. I didn't know exactly what that icon was. Well, that seems accurate. All right, so you got 2.69 million for every 1 year. You got to convert what? Years to days? You got to convert days to hours. And then hours to minutes. There's 3 numbers there. 365, 24, and 60. And if you think about it, is it getting larger or smaller? If we're going from deaths per year to deaths per minute. That should tell you what to do with those numbers, kind of. If the unit analysis doesn't. Oh, okay. We just got one more. I think there's one more problem after this. Is that right? And they kind of, I think it's just broken apart into multiple parts. Where are we at? 55. Oh, no, we got 3 more problems. Okay. That last problem's got like multiple parts. Or the last few of them do, I think. Oh, went too quick. I didn't even look at what happened. Oh man, what are we doing? 5.12, 1.45. 5 is pretty close. 50, I think you're off by 10 somewhere in there. I'm not seeing where that 1.4. All right, so I said 365 and what? 24, and we have 60. Those are the conversion factors. Oh, come on. I thought this, like, I thought this one was an easier one than those previous ones y'all were getting right. If I'm being honest. I thought you were going to get this one. Okay. So the first thing, I want to convert my years to days. I know that's 365 days in a year. I know 1 day is 24 hours. I know 1 hour is 60 minutes. And so what this is telling me is I should divide by all of these things. Did someone not convert that? Maybe someone didn't convert the 2.69 because this is million. So that might have been something that happened. I'm trying to think of how you got those other numbers. I'm not sure I'm seeing it. But rounding it to 2 decimal places, it should be 5.12. Are there questions about this? So you can do this with unit analysis, but if I'm being honest, I feel like you might even be able to do this without unit analysis, right? We know we start with a large number of deaths per year. We know we should be getting smaller if we're talking about deaths per minute. And so we should be dividing each time. There is an order you have to divide things in, maybe. Maybe that might be where some people are messing up. right? We can't just divide these two things and then, like divide that. There's a sort of order you got to do things in, maybe. So that you're not dividing stuff that you should have multiplied, or vice versa. Cells in human body, estimate the number of cells in the human body. Ooh, this one. Estimates of the number of cells in human body vary over an order of magnitude. Indeed, the precise number varies from one individual to another and depends on whether you count bacterial cells. From my understanding, most of the cells that you're composed of are probably not either bacteria. But there we go. Here is one way to make an estimate. Assume that the average cell has a diameter of 6 micrometers. So I'm going to give you a little hint. If 6 micrometers is 6 times 10 to the minus 6, 1 micrometer is 1 times 10 to the minus 6. So that's what that sort of information is giving you. 1 micrometer is that many meters, is what that's also telling us. Which means it has a volume of 100 cubic micrometers. How many cells are there in a cubic centimeter? Okay, so there are basically, I think there's 3 pieces to this puzzle. There's 1 micrometer is 1 times 10 to the minus 6 meters. The other thing is we want to talk about centimeters. And so that one you should kind of know, but if you don't, there will be that chart. That's one you might know, right? Centimeters are pretty common. So 1 centimeter is equal to basically 1 times 10 to the minus 2 meters. So it takes 100 meters. So this would be what? 1/100th of a meter would be 1 centimeter. Or you could say 10 to the positive 2 centimeters would give you. That's the other way. Either way you want to do it, you should be able to get there. The other way is saying 10 to the positive 2, 10 to the positive 2 centimeters is equal to 1 meter, or 100 centimeters is 1 meter. So you can use one or the other of those. So we're going to want to use basically, come on, drawing. This is one bit of information. This is another bit of information. Use either one, not both. And then the other thing that they give us here is that 1 cell basically is 100 cubic micrometers. So 1 cell and 100 cubic micrometers. 1 cell and 100 cubic micrometers. This thing, I'm going to tell you right off the bat, like this thing has some unit analysis in it. So buyer beware. You're going to be putting these things multiple times. It says cubic. Cubic means to a power of 3. So you got to be careful with your conversion factors on this one. But here's your 3 bits of information. We want to start out with 1 cubic centimeter. We want to end up with cells. So start out with what you know. We know 1 cubic centimeter, which is 1 centimeter by 1 centimeter by 1 centimeter. Discuss. No. Go for it. Okay. 10 to the minus 6. I feel like this is probably the hardest one in this one too. After we get this little conversion factor, I feel like the other ones just kind of fall from getting this one. But maybe I'm wrong. What is the micro? Is that the little? I think it's a little a mu prefix, isn't it? Yeah, it was a mu. The Greek letter mu is what they use for that. I think your solution should just be a power of 10. So I think if you just put the 10, I don't think I even put the number out in front. I think I just put 10 to the power. Everything else is just ones. I can't see nothing on the screen here. Okay. Oh, wait, yeah. No, wait, no. That's it. Spider. And there are multiple ways to do this. Because I use meters as the sort of middle guy here, I think. I went from cubic centimeters to cubic meters. And then I go from cubic meters to cubic micrometers. And then you should be able to go from cubic micrometers to the number of cells. She sells C cells. We're at 2. Got 2 more people. Are y'all trying something?
I'm trying, but I'm still confused.
We'll go over it in the next slide.
Okay.
I feel like this one's a lot of writing, but if you know what you're doing a little bit, it makes it really easy. Or maybe not really easy, but it makes it easier. That's what I should probably say. Like with the powers of tens and stuff, it goes really quick if you know what you're doing. Says the guy that's been doing it all his life, but yeah. We got 3. One more person. I'll just try something. Was that Richard? I think you're the one that's talking to me, huh?
Yeah, wait. I'm gonna try something real quick right now.
Okay. Let me clear this thing off. Oh. All right. Let's go. Let's look at the thing then. Are you still working?
No, yeah, I'm pretty sure mine's completely wrong. So
It's fine. It doesn't matter. We'll see if you got it set up. See where you got getting it. There's one. 10 to the 10. What are y'all telling me? 10 to the 10 is what it should have been, I think. 6. No 6 in there. The 6 is for the 6. If we're doing just 1 nanometer, it's just 1 times 10 to the whatever. Right, 6 times 10 to the minus 6 is for 6 micrometers. If we're just doing 1 micrometer, then it's just 1 times 10 to the minus 6. So we start out with centimeters. And this is like I was saying, there's basically 2 different ways you can convert the centimeters. I think I put 10 to the second as a positive on the bottom. You can put it as a negative power on top. It's the same thing. But these are on top. If I wanted to write these all over 1, I could do that, but they're basically on top. So if I'm converting centimeters to meters, I think I'm getting 10 to the 6, 2 plus 2 plus 2 on bottom. So I converted my centimeters to meters. That's what this first fraction is. Now I want to convert my meters to micrometers. And so this is the dimension analysis. I have to do everything 3 times if I'm talking about cubic. And so what this is doing is 6 minus 6, I'm going to have 0. Minus 6 and minus 6 is going to give me minus 12. And so it's minus 12, but the other important thing is to notice it's got to be on bottom. So now I am in cubic micrometers. This gets rid of my meters, the previous thing I did. Right here, my meters is going away. So now I am in cubic micrometers. From cubic micrometers, I want to go to cells. So cubic micrometers. Now I am in cells. I'm probably going to look at 100 as being 10 squared. So in my brain, I'm just converting anything that's a power of 10, I'm converting it to a power of 10. So what I'm seeing here is a minus 12 plus 2 on bottom. What should give me minus 10? And I talked a little bit about this in the notes, but 1 over 10 to the minus 10, what the negative exponents mean is that we're flipping them, basically. So if I wanted to, I could put this thing over 1. I don't have it written here, but if I really wanted to, you can think about that as being over 1. So what you end up doing is you end up flipping them. If they're in the numerator, they come in the denominator. Denominator goes to the numerator, and your exponent becomes positive. So this should be giving me 10 to the 10th power, or 1 with 10 zeros there, basically, right? Okay, questions about this? I know this one's pretty involved. We got to convert to meters. There's 2 conversions here, basically, and 3 conversions. Okay. So part B. Once you answer part A, I believe part B is like probably, I feel like this one has less steps if I remember correctly. So estimate the number of cells in a liter using the fact that a cubic centimeter is equal to 1 milliliter. And we know 1 cubic centimeter is 10 to the 10 cells. So what it sounds like is that we need to start out with a liter. We need to convert to a milliliter. 1 milliliter is the same as a cubic centimeter. We can convert from a cubic centimeter to cells. There are 1,000 milliliters in 1 liter. So that might be something you need. 1,000 or 10 to the third. Either way you do it.
You said 10,000 for a liter?
There are 1,000 milliliters in 1 liter, or 10 to the third.
Okay.
So this, your solution to this should also be a power of 10. So I don't need that number out in front. I just need the power of 10. Now come on. So I think really the only thing you have to do is convert liters to milliliters, and milliliters is cubic centimeters. So then you're converting cubic centimeters to cells. I think people studying like nautical history, when they like collect those little fragments from the linen they use to catch the wind, you think they sell the cell cells to be analyzed? You know, she sells cell cells. Sorry. All right, so there should be, oh, there's 4 fractions you got to write out on this thing, so maybe it is a little bit difficult, but there's like one step. Where are we at? 2 people, okay. I think we're just getting larger and larger here. We're going from liters to milliliters. We should be getting larger by what, 10 to the third? And then once we're in milliliters, we should be getting larger by 10 to the 10th. If we put those 2 together, I think we get larger by 10 to the 13th. Is that what we are getting? Or are y'all way off? What's happening? Way off. Maybe not. 10 to the 12th. Oh, so close. Yes, that is close. But you got to put these things together, right? When we multiply like bases, we're adding our exponents. So it should be 10 to the 13th. Again, this is this thing laid out. So basically what I'm seeing here is that this thing, I'm probably going to look at this as being 10 to the third. And so this is what I was seeing with your notes. You're saying 10 to the third times 10 to the 10th should give you 10 to the 13th. I was seeing where that's coming from here, hopefully. Like I was saying, this gets rid of liters. This will get rid of my milliliters. This will get rid of my cubic centimeters. And I should have something in cells. Questions about this one? Okay. The next one. Cells in the human body, part C. Estimate the number of cells in a 70 kilogram person. Assume that a human body is 100% water. It's really not. And that 1 liter of water is 1 kilogram. We know 1 liter is 10 to the 13th cells. So that will help us. I should have wrote that in here, but I didn't, I guess. So what it sounds like is we want to go from 70 kilograms and we want to figure out how many cells that is. So what are we going from kilograms? It looks like I'm using the fact that 1 liter of water is 1 kilogram. And then it looks like I'm going from 1 liter of water, and I'm using the fact that I know 1 liter of water is 10 to the 13th cells. And then I got to do a little bit of shifting around to put this into scientific notation. Remember, I should have 1 number out in front. So this one is going to have a number out in front. Here we go. Are you getting the right answer? Just not putting in. Yeah. Oh, yeah. Yeah. Good. That's the correct solution. It's just it's not in scientific notation, basically. But that is the correct solution. In order to put it into scientific notation, and this is the thing I was gonna say, like this one's getting smaller. This one has to get larger. So y'all did that correctly. It looks like everyone got the correct solution. It's just like you just clean up into scientific notation. Was like just the one issue that happened there. So sometimes you got to look at your solution, see if it's in scientific notation at the end. But this is what y'all did. So y'all know how to do this. You already did this. 10 to the 13th, 70 times 10 to the 13th is what you're going to end up getting. You got to clean it up a little bit for scientific notation, but it's there. Next one, come on, slides. Hey, this Amazon one. They love National Geographic in this book, apparently. And National Geographic. What does it say? Something about the Amazon drains a sixth of the world's runoff into the ocean. One day's discharge at its mouth is 4.5 trillion gallons. And this could supply all U.S. households for 5 months. Based on the statement, determine how much water an average U.S. household uses each month. Does this answer seem reasonable? Explain any estimates you make. So the book assumes there are 100 million households in the U.S. There's somewhere around 328 million people, I want to say, in the U.S. or something. Let's see. It was like 328, I think, right? Yeah, there it is. So I guess they're saying households are about 3.2 people, whatever that's worth. But they're going to assume there are 100 million households. We have 4.5 trillion gallons. And that's enough for 5 months. How about each month is what this is asking. So if there are 4.5 trillion gallons, and we're dividing that into 5 months, and we're dividing that into 100 million households. Thousands, millions, billions, trillions. That seems right. Guys. Oh man. So 4.5 trillion, you divide it by 5, you divide it by 100 million. What are you getting? That's what we're doing here. They're talking about this is enough for 5 months. So if we want to know per month, we're dividing this. If we want to know each household, and there's 100 million households, then we're dividing by 100 million. So we should be getting 9,000 is what it should be. $9 trillion. So you gotta make sure you put enough zeros there. What are y'all telling me? I didn't even look. $9,000. That's it. 9 times 10 to the third. Y'all got it correctly. It just the computer's being angry. All right, 69, personal consumption. The Bureau of Economic Analysis estimates that in 2015, personal consumption expenditures of Americans totaled 12.3 trillion. The major categories in these expenditures were durable goods, non-durable goods, and services. So basically, they're going to take all our expenditures and they're going to divide it up into basically 3 different categories here. And then they're going to ask us something about percentages, something about something or another. What is the approximate annual per capita spending on personal consumption if you're going to assume the population is 321 million? So I just wanted nearest dollar amount for this thing, apparently. But coming back up here, they are talking about personal consumption. The personal consumption was the overall 12.3 trillion. So if I take 12.3 trillion, thousands, millions, trillions, and I divide that into the households, what am I getting? So I believe what I'm doing is I'm looking at what the 12.3 trillion and the 321 million. I want to know how much per household that thing is. Okay, I'm not spending every day. Like, come on, yeah, like I'm not trying to spend all day in this class. Okay, what are we doing? 3, 8, 3, 1, 8. That's right. 38,317. That's right. That's right. I think maybe I just didn't put a money sign in there or something. I don't know what it did. We're just dividing those two numbers. The next thing, what are they asking? What is the approximate daily per capita spending on personal consumption? So if we got 38,318 annual, and we want to know what the daily spending is, what is our daily spending? And this is to the nearest whole dollar. All right, now I'm going to give y'all like 15 seconds on this, maybe. There's one thing you got to do. You got to convert annual to daily. Okay. So divide by 365, you should get 105 is what you should be doing there. Okay. Personal consumption, what are they asking now? On average, about what percentage of personal consumption spending was devoted to services? So this is to the nearest whole percent. Personal services, this is kind of a review of last section. So devoted to services. So I believe services is 8.3. Personal consumption is 12.3. So I'm going to give y'all a few seconds, but we want to know what percentage this thing is of this. So what percentage is services out of, so 8.3 divided by 12.3 is giving me what, 67%? And then the next thing is another percentage. About what percentage of all personal consumption spending was healthcare? Did they give us a number for healthcare? 2.1 trillion. So spending on healthcare was 2.1 trillion. About what percentage of all personal consumption would that be? So nearest percent. So should take you 10 seconds, hopefully, if you're doing it. 2.1 trillion is what percent of 12.3? This is what they're asking. Oh man, come on, dudes. Are y'all trying to stay here all day? What's going on? I guess like I don't understand like why people lag this class so much. It's like, you know, we have like a set amount of work to get through. We get through that work, that's all we got to do for the day, right? Like, have y'all not figured this stuff out yet? Like, I don't know. I think some of y'all might have figured it out. Some of y'all seem like y'all don't even know you're taking a class. Like I don't know what's going on this semester, but it's not good for a lot of people, and it's not everyone. So take it for what it's worth. But there we go. Yeah, you just need to convert that to a percentage, but that's right. Should be 17%. And personal consumption. Okay, what are they asking now? In 2000, the total spent on personal consumption was 6.8 trillion. Healthcare was 918 billion. Compare the percentage increase in total spending in healthcare, in total spending and healthcare spending in 2000 and 2015. So we're going percentage increase. So if they're talking about a percentage increase, we talked about two different ways to talk about increases. One of them was absolute and one of them was relative. So if they're talking about a percentage increase, they are talking about relative increase. So it looks like we are going and looking at total spending. My total spending here is 12.3 trillion. And that's coming up from 6.8. And I'm rounding this to the nearest whole percent. So I think they're asking about the relative increase from 6.8 trillion to 12.3 trillion here. So how do we find relative increase?
Wait, would 6.8 be the new value or?
This is the old one. We're going from 6.8 to 12.3. Because this is the year 2000. This one was the year 2015. So I believe this should be the reference, right? 6.8 should be 12.3 minus 6.8 divided by 6.8. I believe is what we're doing. Is it coming through? I already submitted mine. I think it's just not loading it. Come on. Yeah, so we're doing the relative increase between those two numbers. We did relative increase last chapter. So I think it should give you something like 81%. Is that what you got? What did you get? 1.9? I'm not sure I see that. Should be relative increase, right? 12.3. Am I going crazy? 12.3 minus 6.8 divided by 6.8. That should be giving you 81%. And then the other thing is what, 918 billion. And that's going up from what we had in the previous problem, which was what? Shoot. Yeah, clear all drawings. Clear this, get out of my way. What was that we had in the previous problem? It was in slide 30. ABC, I believe is this one. What did they say? It was, no, maybe it was the 31. Was this one that had it? I meant to say 2.1 trillion was healthcare. So 2.1 trillion 2.1 trillion, and it started at 918 billion. Let's see. So I think we got to convert them either to like whole ones or something. I personally would probably put things in billions. 2.1 trillion is what, 2,100 billion? I think that's what I did, 2,100. And we're going from what, 918? And we're dividing that by 918. I guess you could put all those zeros there if you really wanted to. But they're just going to simplify out. That's just coming from the fact that 2.1 trillion is 2,100 billion. All right, so that is the last one. Are you going to make me be the only one answering this? All right, so let's see if it's, what did they say? Did I get the correct answer? This was stuff we did last time. This is relative change. Trying to make sure you remember it. You should have got 129% is how much that goes up. And so if we compare the two, I think our healthcare is going up like way more than everything else, right? It's a ridiculous scam. I don't know what else. All right, that's it. That's all I got for you.
Have a good day.
Yeah, take care.